Incorporated as a whole is one of the top steel fabricators in the United States. We've got about 11 different divisions all across the Southeast, a plant in Oklahoma, and a new facility in Oregon. We were founded in 1955 by Glenn Sherrill, who started off just as a stair and rail fabrication facility, and has grown that to now probably over 1,000 employees at about 16 locations around the Southeast, Texas, and Oregon. And we are privileged to say we're still a family-run company while maintaining those same core and values that you get with a family-run business. That's actually a picture of our facility. It's actually in Emporia, Virginia. So if you go up 95, about 13 miles north of the North Carolina border, you will see Highway 58, and our plant is about a couple minutes off of 58 once you get off the exit if you're heading towards Virginia Beach. So if you've ever headed to the coast, if you look to the left, you will see our facility over there. You can see we recently installed some solar panels to help make our facility more environmentally friendly. You can see kind of the material stacked there in the main yard, and we've got a second shop bay that we just built across the road that you can see in the upper left-hand corner. So we are, again, one of about 7 plant facilities that SteelFab as a whole incorporates into the bigger family. So we are a structural steel fabricator. We are what's considered a first-tier subcontractor. So in the hierarchy of construction, in the world of construction, you have got an owner, somebody who is looking to build, an office building, or a college that is looking to build a new, arts and science building. And so they reach out to the design team, an architect and an engineer to help develop plans, as well as a general contractor to help manage the construction aspect of that project. And then through bid processes, negotiations, pricing rounds, they will bring on subcontractors. So you've got MEP trades, concrete, site work, finishes, and we just kind of fall into the structural steel portion of that tree. So we answer kind of directly to the general contractors. They are considered our customers. But SteelFab is unique because we also offer a lot of value and give a lot of feedback to both the design team, working with designers on efficiencies for steel design, as well as developers who are looking to build and expand on their facilities. What does a steel fabricator do? So we are not a mill. We do not produce the steel. We buy the raw steel in its just basic form from a mill. Some of these big cast iron mills taking recycled products and melting them and molding them into steel shapes. You may be familiar with I-beams, channels, tubes, plate, angle. So we take that raw material and we buy it from the mill on a per project basis. So we're not just loading up on random material that we hope we need. Every purchase we make is coded to a specific job for that specific purpose. And so we buy the material needed for that project. We detail every piece of steel. So when we get the plans from the engineer of record, they have designed the overall building structure based on the load requirements imposed on the building. It has been our job to hire a detailer to actually go through and compile drawings for every piece of steel that will help make up that building. So that's the columns, the beams, the girders, edge plate, kickers. Every component needs to be detailed on a drawing, and we send those to our shop to fabricate that material so that when we send it to the site, it goes up and is erected as it was planned to on the original contract drawing. So that entire process, from the time we're awarded a job, from the time the materials is on site, can usually take anywhere from 10 to 16 weeks, depending on the size of the project. And then we are asked to subcontract the steel erection portion of our scope of work. We do not self-perform that work. So if you see cranes, iron workers, guys climbing steel, we sub out that work to steel erectors. So they will work with us on submitting quotes and bids to get awarded that project, just like we do for the general contractor, and we hire them on board and help manage that scope of work as well. And so once the material delivers, they can take anywhere from 4 to 18 weeks, depending on the size of the job, to erect a building. And so you can see it from its raw state to the fabrication stage to then the finished product. And I included a picture here of the cathedral off Western Boulevard near NC State. That was just a steel project that we did that we're very proud of, that you can see there in the picture. So that's kind of the finished product of the steel framing there. So here at our office in Raleigh, we have a variety of roles that people have careers in. We have got sales and estimators, folks who are actively seeking new work, putting pricing together, and submitting bids and budgets to our customers. We've got project managers who take over and manage jobs once they are awarded, and go through the logistics, coordination with general contractor, work through schedule, help make sure that drawings are issued to the shop on time so that we can maintain our production in Emporia. We've got our fabrication facility up in Emporia, like I mentioned before, that consists of about 95 blue-collar workers who work in the shop on 2 shifts, as well as about 20 office staff up there who help run the day-to-day of the staff up there. We also have connection design, so engineers on our payroll who review steel-to-steel connections and help design those components of our work, and detailers who are responsible, like I mentioned before, for taking what is shown on the structural drawings and putting them together into usable detailed drawings that we can fabricate off of. So running through, again, just kind of the sales component of it, again, trying to find projects that meet our strengths, and that can be market dependent. Obviously, we are in a kind of a turbulent time right now, and so the market is a little tighter. We may be venturing out into areas of work that we typically wouldn't, but when we're trying to find work, we go to where we need. SteelFab offers a unique service, we like to say, that is just more value than just a quality of fabrication. We work directly and collaborate with contractors and design teams to help make the project as efficient as possible from a monetary standpoint, and also schedule and site logistics. And I think that value is really recognized in some of the larger work, some fast-moving projects like data centers and pharmaceuticals. And so, some real basic office building work that anybody can do, we may not always be selected, but when there are difficult coordination drawings or site logistics that need to be worked through, we are usually asked to give our input and at least explore opportunities there. Estimating, as I mentioned, this is doing a takeoff of all the steel components of the drawings, picking up all the scope that our customers would expect from us. And so they are taking that information and putting that into our pricing managing tool online, and using the output for steel pricing and shop production, along with some other components, to develop a proposal that we then hope eventually becomes a job. Design and detailing, I went through that earlier. Just again, some engineers and detailers who are going through models, working through BIM coordination, and with our customers to help ensure that we don't run into any clash problems in the field with other trades, whether it be MEP or other subcontractors, to ensure that we can resolve any problems through the model and on paper before it becomes more costly in the field and impacting schedule once these items go up. And then, of course, project management, communicating, coordinating, and developing logistics with the contractor and our customer. The fabrication in our plant that occurs for each project that we specialize in. SteelFab, we're in a unique position because we require, college level graduates, folks with, degrees from Wake Tech, NC State, Appalachian, those types of schools to, we're really looking for estimators and project managers to help come in and work for us. But we've also got some real opportunities for folks who, college just isn't a great career path for at our shop. We have got a production manager up there and a few leaders who have really grown through our program up in Emporia that offer opportunities for young folks who are responsible and just hungry to work, and they can really flourish with a company that offers 401k benefits and healthcare and dental and all the benefit packages you would get from going to a place where where you're going to work every day, and can really set a nice career path for somebody who doesn't necessarily see college in their future. So, just because here in Raleigh, we may be looking for a different type of skill set, someone more, with a college or mechanical engineering background, math background, there are certainly other opportunities for those folks at our plant in Emporia, and we're always looking for good folks who are responsible and hardworking to help bring up leaders there, because sometimes that's a challenge, that's a struggle. I mean, we try to pull from the local community there, but it's not a strong area, and so trying to find folks who will come to Emporia to work and who are willing to do that, it's tough, but those who have, and we've got a few success stories, have really made a good career path for themselves. And we've had folks in other plants flourish and come up to be plant managers or assistant plant managers. And they started out as a fitter or a welder, and they just worked hard and kept at it. So kind of two different areas of opportunity, but with the same, attractive benefits and growth career path that you get, whether it's Raleigh or Emporia or one of our other locations. I just thought I'd add just a few local jobs here that SteelFab has participated in. Raleigh Union Station up here at the top, the old Dillon warehouse building that was transformed into the new train station that we have at the corner of town. State Employees Credit Union here in the lower left-hand corner, about an 11-story tower on top of a 6-floor parking deck. This shot here is one of called Wynn Glenwood. It's one of the first of the two towers going at the end of Glenwood Avenue downtown, if you've ever been down there. This new MetLife building, which is on the backside of Weston Parkway. It's a pretty cool shot of that building. And then this is kind of a neat panoramic view of the Durham Bulls Athletic Ballpark. We were fortunate to play a part in a variety of projects you see in this picture, including the Durham County Justice Center there in the back right-hand corner. These office buildings that surround the outfield. At the time, they were called Diamond View, but they're essentially just big office buildings. When the Bulls expanded their scoreboard, we had a part in that. When they raised the bull that lights up on home runs, if they need some extended steel columns, we had a part in that. We also played a part in extending the right field facade. If you've ever been out there with the kid area and the other Bulls shop a few years ago. So all those requiring steel components, we had a part in. So pretty neat stuff. You're able to see a lot of diverse projects. As a project manager, we work on usually about 6 or 7 jobs at a time, as opposed to like a general contractor who's focused on one project for like 2 to 3 years. So it's kind of fun. It adds a lot of excitement and variance to your day, having jobs at different points and being able to see different things that impact your community.
I graduated from NC State with a material science degree, specialized in metallurgy, and worked in construction my senior year, on and off with classes. So when I heard about SteelFab, I was pretty excited because it's pretty much a combination between what I knew about material science, but mostly about the construction area and management. And I've been here for about a year, and about 6 months ago, we got really started on what will be 3D coordination, virtual coordination and computer design. So we don't only coordinate with the plans that we get from the engineer and the architect with the client and the other trades, we also are able to produce a full steel model from the building on a one-to-one scale that they can use to lay out walls, lay out piping, lay out HVAC ducts ahead of time. So that allows general contractors to save a lot of money down the road, preventing clashes in the field. All of these clashes can be discovered online, fixed, rerouted, and then when the guys get to the field, most things fit as intended. So it's been a really good year here. I've learned a lot about estimating and steel. SteelFab is one of the largest fabricators, but really gets that tight mesh, tight community feel, especially here in the office. You can see people popping in and out everybody's offices. And it's really nice to be able to work on different projects across different states or different contractors to learn what practices are used in different construction companies. I didn't think that the construction industry was as dynamic as it is these days. I thought it was very much streamlined. You get your plans, you produce what's in there, and you erect it. But the amount of coordination that goes into these and the amount of design and engineering that goes into these buildings is ever increasing, and it's really exciting to see that happening from your computer, where you can see a model, you can see a beam, to when you go to the site and you talk to the directors and see the building go up.
You know, Eloy has really started to pursue the building information modeling system that has become really important in the construction industry, and importing models and navigating through those models to help resolve problems before they become problems in the field. So we're being asked more and more to participate in those meetings and have those conversations. As a structural steel supplier, there's only so much we can really manipulate in the model without affecting the structure itself. So if you have a piece of conduit going through a 24-inch deep beam, you're not going to ask the steel guy to move his beam for the conduit. I mean, the electrician's going to have to move around. So we've been limited in what we need to do there, but more and more is being asked of us as drawings become less and less complete early in the stage. Projects start sooner before 100% drawings are issued, and so we're having to navigate through these problems a lot sooner, and Eloy has been a huge help in helping bring SteelFab up to speed on that.
We tend to start people in estimating, whether they're going to be an estimator or a project manager, just to get used to the drawings, to get pricing, and I was used to reading architectural drawings, so wall layouts, ceiling layouts, light layouts, but I never had to think about the structure of the building. So when they give you a set of drawings and they tell you price these, it's not only pricing what's on the plan, you also have to use for the most part, experience, or the experience of your senior estimators, to figure out, okay, they're connecting these beams together, they're not telling me how they connect. You got to provide that material, you got to price that material. So that was probably the biggest hurdle for me the first few months, is learning how to interpret those drawings on a logical manner. It's not just what they're showing. With construction moving faster and faster, we get 70% drawings, 50% drawings, to sometimes award us a contract. And we price the sets as they come out cleaner and cleaner. But you still gotta approach them logically and tell the client what you see in the drawings, what you think they're missing. And sometimes it's an allowance, sometimes is you just exclude it altogether because it's not shown. And helping the client realize what's missing in the drawings early on helps a lot. And that was the biggest hurdle for me as I started here.
I'll echo that struggle. That's something with our co-ops and interns, because we do have a co-op program here at SteelFab where we partner with colleges to bring on students for rotations, and that's the biggest struggle and hurdle we have to go through with the students, is to help them visualize the plans. You can kind of see, the plan on paper and see it in 2D, but can you visually understand that, a section cut on the perimeter tells you to go to detail A on another drawing, and can you go there and kind of visually transpose and say, okay, I got to flip the building up and see what's going down this row here. And sometimes that's hard for folks without that experience, and that way of thinking, to just be able to interpret those drawings, as Eloy mentioned.
With English as a second language, it's sometimes complicated finding the right word to use. A lot of the times I will draw something and put an arrow to it and say, what is that? How do you call that? Because it happens every now, it happens less these days, but it's happened to me a lot the first few months. I didn't know what the steel world called a specific item or tab. So using the proper terminology, not just within the company, but when you're on a phone call with a client and they call a beam something else, and you're, wait a second, let's take a step back. Can you show me in the plans what you mean? Because that means something completely else from the steel world. So communication skills for sure have been a fundamental part of this industry. And I think any industry that requires coordination, which is any industry, it's going to be more and more in the future the rule of the baseline.
We wanted to give you guys an idea of what our engineering group does. We've got a group of engineers in Charlotte who work corporately for our offices. And so, as I mentioned before, when we get a set of plans, the structural engineer of record has designed the building. So he's taken information from the architect and other components to design and consider live and dead load and wind drifts and things of that nature, whether the job is seismic or not, and design the main steel members along with slab thicknesses and footing depths and so forth. And so that component of the drawings, that is already presented to us. So we don't need to analyze any of that. But what we are asked to do is design and develop the steel-to-steel connections. And so that's really twofold. It's one, to kind of take the liability off from the engineer of record, but also two, it gives the fabricators some ability to help design connections that are practical and help fit into the streamline of what works best in their shop. So you may have different steel fabricators with different philosophies on what type of steel-to-steel connections are more efficient, and so that can vary by shop. And so for us, we typically use a single, what we call a shear tap plate, and we've got standard plate sizes that we can apply based on different loading requirements that we can just run those parts, and regardless of project, we know the size of that part and we can put it on the beam. And it just helps us make be a little bit more efficient in the shop. So if you think about, creating a pizza or something and putting the toppings on, if we know the same toppings are going to be put on each pizza, you can kind of streamline that a little bit more. But if you vary the topping by each pizza, it just becomes a little bit more rigorous, and so you spend a little bit more shop labor on each project if the connection design criteria is different on each job. So we try to be as seamless as possible when developing our connections. And so what we wanted to do here is give you guys an example of that. The purpose is to demonstrate how SteelFab engineering takes load information provided to us by the engineer of record to develop steel-to-steel connections while accounting for economics. And so, like I said, the engineer of record would show the main steel members on a plan, and they may show, they should show a little notation by each piece on each end with the number. So it may say 10 or 15 or 30. And what he's designating there is the load for that piece at that end. So he's saying, you know, a piece may have a 30 kip reaction at each end of the beam, and so that is the load that we need to design for. And so we'll get into that here in a little bit. So below, I included a picture. What we're going to analyze today is a vertical brace frame. So it's the side of the building that is braced by steel members. So you've got some steel members here in the photo. This is called a V brace or a chevron brace. Sometimes you'll see a single span brace that may span from one corner to the next corner. So those can vary in design and shape and complexity. I just kind of pulled this from an old job, but below this picture, we've got a model of a 2-bay, 3-story steel frame building. So we Katie helped kind of conceptually design this little structure here. So you've got a 3D picture, if you can imagine this. So you've got braces on one side to help with the forces being applied laterally to the building, and then braces on the back side, which is these dashed lines. And that kind of goes back to, are you able to visually see kind of what's going on here in the building? So you've got these braces in front of us, and what we want to do is analyze the forces given to us and design connections for each of these braces. So the building depth is 20 feet. And there are three different braces with different forces acting upon each brace. So you've got a force, F3 is 110 kips, which kips are a unit of measurement that is equivalent to 1,000 pounds of force. So instead of saying 110, 1,000 pounds of force, we just say kips. So you may or may not have heard that before. It's just basically a unit of force. So F3 is just signaling that the force being applied at this level right here is 110 kips. If you read above, I believe F2 is 100 kips, and then F1 is 90 kips. So the force being applied at the top is the greatest, and then you kind of come down, and we just kind of manipulate these numbers. So it's 110 up here, it's 100, and it's 90 down here. Katie also wanted to point out here that the force acting at level 1 here at this level will be evenly distributed between the two braces. So unlike the top two levels where you only have one brace coming across, the bottom level looks more like the photo I showed you at the beginning that has two braces. So those braces actually take on half of the load. So if you've got, you know, a load being imposed on that level, each brace takes on half of that load. So I'll continue by saying our goal here is to calculate the forces in each brace and the connection plate thickness. And so step one of this activity is going to be to calculate the force in each brace. And so we put those braces, if you refer to the picture above, and I'll try to go back and forth, it's a little tough to follow if you don't just have the document in front of you. So to calculate the force in each brace, so what we need to do, what we've laid out for you to do is to kind of step by step go through these equations to determine the amount of kips that are being applied on the brace. So don't get confused with the force being applied to the side of the building that we gave you above. We are taking into account the force in the brace. Obviously, this helps, you know, what we wanted to do was present some curriculum that would help with vectors and using sine, cosine, hypotenuse, and so forth to help determine some of this information. So Katie also stated that the force in each brace is the geometrical vector of the sum of the lateral forces occurring at that level and above. So basically what that means is that if I go back to the top of our diagram here, the force being applied here at this location, F3, is 110 kips. The force being applied here at this level is the sum of the forces above, if that makes sense. So not only do you have to account to the force at that level right here, but you have to account for the force at the roof. And so those forces are being magnituded as you go kind of down the building to the base level. And what you'll often see if you're looking at a set of plans, is that at the base level, if we're talking about maybe column shafts or brace sizes, those braces at the base of the building, you know, if you've got like a high rise, maybe a 10, 12, 15-story building, those sizes are going to be significantly larger than the ones towards the top of the building. So as you go up the building, you start to maybe decrease steel-sized members because they're not carrying quite the load capacity that you are at the base of the building. So here at this first floor, you will need to add the forces being applied at all three levels, because the forces are all being applied here at this level to both these braces. At the second floor, you'll add the second floor and the roof, and then only at the roof level, you just have to account for the one at the top. And so you'll use that information at the beginning of the paragraph where we gave the kips for each one to apply to the equations below. So, so we've kind of helped outline the steps for you here, which will require some kind of trigonometry math here to find the hypotenuse and the then using, you know, the SOHCAHTOA method, I guess, if you will, finding the force applied to the vector in each condition. So you've got the force in brace 3 at the roof, second floor brace, and then the force being applied at the brace at the base level. So then you're left with 3 answers, basically one for each brace. And using that information, we're going to move on to step 2 to determine what size connection plates to use. So step 2 says Leonhard Euler was a Swiss mathematician, physicist, astronomer, and engineer, among other things. You may have heard of him before. He was credited with developing a formula giving the critical buckling load of an ideal strut, which depends on its length and the stiffness. This is referred to as Euler's equation. It's just basically a kind of a set equation that we're supposed to use to determine the maximum compression for different plate thicknesses before buckling occurs. And so we include this diagram down here kind of as a blow-up shot of what is happening at the connection that we need to design for. So you've got that brace there that we saw in red in our 3D schematic sketch up top. So that is the brace. And what we're doing is trying to account for, well, what size thickness does this plate need to be? And so using the information on the loads being applied here, we're going to select a plate thickness, the minimum plate thickness that needs to be sufficient for that load. And so using Euler's equation, which helps analyze the compression zone of buckling, basically at what point will that plate start to buckle and crack, we want to factor in the plate thickness in this area of buckling to determine how thick the plate needs to be. And so what we've done is kind of predetermine some plate thicknesses that we commonly buy to help make that decision. And so this formula right here goes through Euler's equation, and we outline some of the variables, many of which are just standard. So E is the modulus of elasticity. You may have heard of that. It's the material strength properties of a component, and for steel, it's 29,000 kips per square inch. I is the member stiffness for plates, which is just the base times the thickness to the third power. L is the unsupported length, which in this case we are telling you is 24 inches. And then A is the area of buckling, which B is again the width of the brace at the compression zone, which we're telling you is 8 inches. And T is the thickness of the plate, which is what we're trying to solve for. And so what we do, just below this diagram, we kind of lay out for you here Euler's equation, allow you to input the data based on the variables that we give below. So you come out with a value times T to the 4th power. And then that T to the 4th power, you will need to plug in various plate thicknesses from the table below to get an output of just how many kips that thickness of plate can restrain. So we're kind of working backwards, and we're saying, okay, for a 1/4 inch plate, for a 3/8 thick plate, for a 1/2 inch thick plate, what is the maximum capacity of that plate in the compression zone? And then using those values, we go back up to the top and say, well, how does that compare to the values that we got from our step one, where we calculated the forces and the braces. And so we compare those two, and then we'll come up with a final determination of what thickness each plate needs to be for each brace.